In this video, we are going to look at the solutions to problems involving the motion of two bodies. Now, question 4 was given to you as a homework problem in the previous video, and I have done a solution here, but I have made a bit of a mistake. In doing the solution, I overlooked the fact that the second aeroplane leaves airport B, and it leaves airport B 20 minutes later after the aircraft from airport A leaves the ground. So what I'm going to do is I'm going to do the solution, go through the solution with you if they both left their respective airports simultaneously. So that's going to mean that the time of travel for each of them until they meet will be the same. And I will show you the solution, and I will then do the graphs of motion. Then I will then give you the solution to this problem where the aircraft leaves airport B 20 minutes later. I will give it to you on Google Classroom. So I am going to, let's go carry on with the solution to the problem, ignoring this section of the problem. So two airports A and B are 1,400 kilometers apart. A jumbo jet leaving airport A travels at 900 kilometers per hour towards B. I've defined the direction of A to B as positive and the opposite direction from B to A as negative. Now, the 20 minutes later, for the time being, we are going to leave that out. I am going to ignore that. So we're going to assume that the two aircraft are going to travel, they're going to be in the air for the same amount of time. So a second aeroplane leaves airport B at 800 kilometers per hour, and it travels in that direction towards airport A at a higher altitude than the jumbo jet traveling from A. So therefore they won't collide in mid-air. At what distance from A do the two aeroplanes pass over each other? So using two data lists for the two separate aircraft, I have that we have aircraft A is traveling at 900 kilometers per hour, and the velocity of the aircraft doesn't change, so the acceleration of aircraft A is 0. Aircraft B is traveling at minus 800 kilometers per hour, and its acceleration is also 0. We're assuming that both aircraft maintain their velocities. Now, what we do next is we look at the position versus time equations of both, and we're going to use the delta more explicitly. Yeah, so delta XA is the final position at a particular point, so I'm going to say it's XAF, and note that what I've done here, which I strongly suggest you do, is that you define a coordinate system. So I'm defining the position when the aircraft leaves A, when it's in the air. We're not taking into consideration its takeoff and that. We're making some broad assumptions here. We're looking at once it's in the air, its position once it's in mid-air. We're assuming that once these two in mid-air, initially they are 1,400 kilometers from each other. Now, its initial position is 0. I'm using the x-axis to the right. So airport B, according to that coordinate system, would have an x value of 1,400 kilometers with respect to airport A. Now, at a certain time, after a certain time, the aircraft A will be at position XA, which is a function of time. I'm using the f of x notation, so x of t, x is a function of t, it's going to increase as time goes along, we find that aircraft B starts off at 1,400 kilometers, and it's going to move in this direction, so its x value is going to get less as it moves closer to airport A. xb of t is a function of time, because it too is going to vary as the aircraft moves further away from aircraft B. So using these two, using delta x equals v initial delta t half a delta t squared for both, and I use subscripts for aircraft A and aircraft B. By the way, I've just said aircraft A is the aircraft flying from that left off from airport A, and aircraft B is the plane that left from airport B. Now, looking here, using delta XA, XA final would be where the X value, where the aircraft is after time t. The initial position of aircraft A by definition was 0, whereas if we see for aircraft B, its initial position was 1,400 kilometers, and then after a period of time, xb of t would be its final position, not in total but over that time interval. So these two values here are actually functions of time, as we will see. The initial velocity of aircraft A is 900, aircraft B is minus 800. Remember, velocity is a vector, so we must assign a direction according to our sign convention, and then delta t, ta minus t equals 0 is delta t for aircraft A, tb is the time that aircraft B has flown minus its initial time t equals 0, and by the way, tb and ta are going to be the same for the time being in my adjusted problem. If you are, when we look at the original problem, then this t value here, the initial t value, is going to be 20 minutes and not 0 minutes. So 20 minutes, take into account we're working in kilometers per hour, so 20 minutes in terms of hours is 20 over 60 seconds. So in the original problem, this should in actual fact be 1/3 of an hour, which is 0.33 recurring hours. And so then you would get an adjusted equation, a more complicated equation for the value of, or the expression of xb in terms of t. But that solution will be provided to you outside of this video on Google Classroom. So now, working with what we have now that xa, which is a function of time, equals 900 ta. So you can explicitly see that as ta increases, xa increases. That makes sense. As the time increases, the x value is going to move along here as the plane is moving further away from its original position. Let's look at xb. xb minus 1,400 is going to be minus 800 tb. All right, and that, if you take the 1,400 across, what you see is, because time is positive, the 1,400 is going to be where it started, and then there's going to be a term which is negative that's going to be taken off as xb gets closer and closer and closer to airport A. So now we've got two equations in A and B, and by now we should know that we solve these simultaneously. You can also use elimination, and now we see that when plane A crosses plane B, then the times will be the same, which will not be the case if we had solved the original problem, and xa will equal xb. So letting ta and tb equal t, we then have 900, we have 900 t, because xa is 900 t, And because xa and xb are equal, we can substitute this 900t in place of xb, because xa and xb will be equal. 900t minus 1400 equals minus 800t. We take the minus 1400 across, we take the minus 800t across, we get 1700t equals 1400. We divide in to 1400 and we get that t is 0.82 hours. So that's the equivalent of 49.41 minutes and or 2,964.71 seconds. If we substitute this value then, t equals 0.82 hours, into equation A, which is xa equals 900ta, then we find that the xa, the value of x when the two aircraft cross each other, is 738 kilometers, because 900 kilometers per hour times 0.82 hours gives us 738 kilometers from where x equals 0. And where x equals 0 is where airport A is. So looking at the question, at what distance from A do the two aeroplanes pass over each other? Well, it's the x value of A when they cross, and we've worked that out from airport A. We've worked it out to be 738 kilometers. Now, thinking about this conceptually, if we now go to the original problem, if aircraft B only lifts off a third of an hour later, then aircraft A is going to travel a lot more distance than 738 kilometers. So expect a value bigger than 738 kilometers, and you should if you've done the problem correctly, you should get a value bigger than 738 kilometers. And aircraft B would obviously travel a shorter distance because before it meets A, because A would have traveled further. So let's now look at the graphs of motion for the simplified problem where we don't look at the 20-minute delay in aircraft B leaving airport B after aircraft A has left its airport. So looking at plane A travels at 900 kilometers per hour in the positive direction. Plane B travels at minus 800 kilometers per hour. It's traveling in the opposite direction. Both plane A and plane B have got accelerations of 0 because we're assuming constant velocity. Plane A starts at x equals 0 because we defined airport A as being in the position x equals 0. And because it's traveling at a constant velocity of 900 kilometers per hour, it is going to have it's going to be a straight line position versus time graph, as opposed to a parabolic shape when you have an acceleration that is not 0. We see every time unit the gradient is going to be the same, the change in position is going to be the same. It's going to be 900 kilometers per hour, and therefore we have an increasing graph. As time goes along, plane A moves further and further away from airport A because x is defined as the direction from airport A. If we look here, we just need to make sure that our axes are labeled correctly. We should always put the unit in, time as seconds. If we look at plane B now, plane B's initial position at t equals 0 was at 1,400 kilometers from where plane A was. Now it's traveling at a constant velocity, but in the opposite direction. So it's minus 800 kilometers per hour. So every hour it becomes 800 kilometers closer to airport A. So therefore we expect the x value to get less, because the x value is defined as the position of the aircraft from airport A. So it does this at a constant velocity, so its gradient is constant, but notice it's a negative gradient, so it's backward sloping. And at 8.2 hours, the two positions become the same. They are flying at different heights, so they're going to cross over. So plane B will cross over, carry on toward airport A, and plane A will cross over and carry on to airport B. And you'll see that here I've actually drawn it such that it doesn't necessarily land at airport A. It might actually travel past airport A. We don't know what its destination is. So if its destination is airport A, and for plane A is airport B, then these graphs should stop here, where, although no, we've got to be careful because they're traveling at different speeds. So certainly plane B would reach the 1,400 kilometers at this point at T. So we can see we can get a lot of information out of these graphs, but this is the key. This is what we were being asked for. We're being asked at what distance. So 0.82 hours. At 0.82 hours, both planes' X positions are 738 kilometers from airport A. So now let's move on to a past examination problem that was assigned to you for homework. So this problem comes from a past matric examination paper, and this is the typical type of two-body problem you can encounter in your matric exams and in your grade 11 exams. So it states stone A is projected vertically upwards at a speed of 12 meters per second from a height of h. Now h is unknown and it's above the ground. So there's the ground and there's h. Ignore the effects of air resistance. So this means we're not looking at any drag. So these objects are going to be in free fall. Object A is going to be purely under the influence of gravity. So even though it's moving up, it's free falling, gravity will eventually stop it and bring it back down. It asks, calculate the time taken for stone A to reach its maximum height. So now it's going to reach its maximum height when its velocity is 0 meters per second momentarily. So using a data list, delta XA is going to be the height above this point, which I've called H star, and that's what we're going to be using that, especially later on when we do the graphs of motion. VA initial is plus 12 meters per second, because plus is up, and that's its initial velocity, 12 meters per second up. VA final is going to be 0 momentarily at its maximum height. The acceleration is going to be equal to minus g, because gravity always acts down, and this object is purely under the influence of gravity, and so therefore the magnitude of the acceleration is 9.8 meters per second squared. Downwards means we have to assign a minus sign to it, and delta t is what we are looking for. We are looking for what is the time that it's going to take for it to move upwards to its final, to the maximum height. So now, using V final equals V initial plus A delta t, V final on its upward motion is going to be 0. Its initial velocity of projection was plus 12, plus the acceleration is minus 9.8 delta t up. Minus 9.8 delta t up we take to the left hand side, and we divide by 9,8 into 12 to solve for delta TA, which in actual fact we are looking for delta TA in its upward motion, and 12 divided by 9,8 is 1,22 seconds. Now they didn't explicitly ask for it, but it's the way we're approaching this section is we are drawing the graphs of motion in parallel to the problems. So it's good to have these values. Not that I would suggest that you do unnecessary calculations in an exam because of the time constraint, but it's good to also see how we use the equations in different ways to get certain quantities that are significant in a problem. So to find H star, using V final squared equals V initial squared plus 2A delta X. VA final on this upward motion is 0. V initial is plus 12 squared plus 2 times A is minus 9,8 meters per second squared. H dash 2 times minus 9,8 gives us minus 19.6 H star, not H dashed, H star. Take the H star to the left hand side, should I say the 19.6 H star to the left hand side, changes from minus to plus, and then divide by 19.6 on both sides, and H star is going to be 144 divided by 19.6 is 7,35 meters. So the height above A, the maximum height above A, where it's projected, is going to be when A reaches 7,35 meters above its original position of projection. Now we read, at the same instant that stone A is projected upwards, stone B is thrown vertically downwards from the same height at an unknown speed V. Refer to the diagram below. When stone A reaches its maximum height, the speed of stone B is 3V. Now, this can be quite challenging and it can seem confusing if you do not draw a graph, or should I say draw a sketch, and if you do not use a data list for each object. So firstly, I'm going to represent the path of ball A, or should I say not ball A, stone A, in red. And I'm going to use a coordinate system where the 0 position value is on the ground level. And the reason why I do this is because both these objects are going to eventually fall down here. I also do it because it means that I don't need to use negative values for any of the positions. If I had to make x equals 0, yeah, which there's nothing wrong with, then the final positions of the balls would be minus h. You can do it either way. I've chosen to make my lowest point x equals 0, which means both A and B, their initial x values, and I'm going to use x instead of y, the initial x values are going to be plus h and plus h at t equals 0 seconds for both. Now, the time is going to be the same for both. You are going to be given a problem where eventually you're going to be given a problem where the two objects are not going to be traveling in the same amount of time. That one of the objects will be projected at a time a little later than the first object, which makes the mathematics a bit more complicated, but for the time being both objects are projected simultaneously, one up and one down. So using red for stone A and blue for stone B, I clearly show now what the different values are. The initial velocity for A is plus 12 meters per second. The maximum height is plus 7.35. So we now look here and we say, okay, TB equals 0. We've spoken about that. The initial velocity for B is going to be minus v, because remember v is the unknown speed. AB is going to be the acceleration for ball B, which is also minus g because it's under the influence of gravity. What we are told is that when the stone A reaches that point, B will have moved down and would have accelerated to 3 times its original speed. It now asks us, calculate the speed v which stone B is thrown downwards. Now, don't panic. Let's take this one step at a time. So let's set up 2 data lists, as I have here. Delta XA is in effect 7,35 meters. Sorry, what I have here is if I was working out the time for it to move up, and that's we've done already in the previous problem, so we don't actually need that now. We have already worked that out, and what happened was I did this calculation and only realized later that I hadn't done it for the first part of the question, for the first question, and so I went and redid it. So this section is actually not necessary here. All right, it gives us, as you can see, the 1,22 seconds, and the reason why we are going to use the 1,22 seconds because it's the time that it actually takes for the ball B to fall from a velocity of v to velocity of 3v. So if we look at the change in position of B, the B is going to fall down. Apologies. B is going to fall down, and it's going to fall, and as it falls down, it's going to be, after a period of time t, it's going to be at an x value xbt, and A will be at xat. So these are functions of time. We did this in the first problem as well in this video. Now, the time that it takes for B to fall under the influence of gravity to go from v to 3v, they tell us is the same as the time it takes for A to reach its maximum height. So we worked this out in the previous example. So in actual fact, this section here, we actually don't need this because we already calculated this in 3.1. So what we have now, the data list here, we have delta xb is the position where it is after time t minus the original position, which was height h. Remember, it was h above ground. Vb initial is going to be minus v. All right, because it's acting downwards, it's falling downwards. There, it's falling downwards. At some point here, let's say at this point here, let's say its velocity now is going to be VB final is going to be minus 3v. Why minus? Because it's still acting downwards. The acceleration is minus 9,8 meters per second, and the time is, well, we've 1,22 seconds, because the time it takes for object A to move from here to there is 1,22 seconds, and that's the same time it takes B to move from its original position, where it's thrown down at minus v, to accelerate to minus 3v. So now, using VB final equals VB initial plus AB delta t, VB final is minus 3 times V, VB initial is minus V, plus A is minus 9,8, times the time is 1,22. Take the minus V across to the left-hand side, becomes plus V. minus 9,8 times 1,2 is minus 11,96. Minus 3v plus v is minus 2v. And now we divide by minus 2 on both sides. Minus 11,96 divided by minus 2 is 5,98 meters per second. Now note, this is the speed. This v is the speed. All right, it's the magnitude of the velocity that it was originally thrown down. So that's not the velocity, it's the magnitude of the velocity that it was thrown down. So we now have answered the question, calculate the speed v with which stone B is thrown downwards. In the next question, 3.3, we are told at the instant stone A passes its initial position. So A took 1,22 seconds to get to 0 meters per second at its maximum height above the ground. And then, because there's no acceleration, there's a symmetry here. The time it takes to move up and the time it takes to come back down to the same position is equal. And the reason is that the distance is the same up as what it is down, and the acceleration hasn't changed. Should I say up here it should be minus 9,8, but it's minus 9,8 for both for stone A and stone B. So now, when stone A comes back to its original position, it's going to be traveling at the same speed but in the opposite direction. So if that's plus 12, that's minus 12. Okay, I'm just explaining in detail so that you get a deeper understanding of what's going on here. The time it takes for A to move up 1,22 seconds and down 1,22 seconds means it's been traveling for 2,44 seconds. Now, it says here, at the instant stone A passes its initial position at 2,44 seconds, stone B hits the ground. Now, stone B was thrown down at the same time that stone A was projected upwards. So that means it takes 2,44 seconds for B to move through the total height. From its initial position, where it was plus h above ground level, to its final position where it's at 0 meters. And recall that our x-axis is such that 0 is here and h is there. All right, so now we want to calculate height h. We want to know what is the value of the original position of xb. So we now said, okay, let's use that equation, the position time equation, which we use so frequently in kinematics. Delta xb equals the initial velocity, vb initial, times delta tb plus a half ab times delta tb squared. I'm going to explicitly use the change as being final minus initial. Xb final is 0, because when this ball is about to be stopped by the ground, it's at 0 meters. Its initial position was, according to the way we defined the x-axis, its initial position was at h. So its change in position is minus h. So another way of looking at it is saying, well, where did B start and where did B end? Well, okay, like this. The change in position is the vector from where it started to where it ended. Its magnitude is h and its direction is minus. So it's another way of looking at it. Now, substituting in minus 5,98 times 2,44 seconds, the time it took for A to move like that and for B to move like that, and then substituting minus 9,8 for A, 2,44 squared for delta TB, we get that minus h equals minus 5,98 times 2,44 is minus 14,5912. Wouldn't be wise to round off to 2 decimal places here. We rather do it in the final answer here. and half times minus 9,8 times 2,44 squared gives us minus 29,17264, which together gives us minus 43,76. Divide by minus 1 or times by minus 1 on both sides to get rid of the minus sign in front of the h. We get that h is 43,76 meters. So this height is 43,76 meters. Now, according to what we were asked, we've answered the question. But what I would like to do, so I'd like to go a little bit further for our graphs of motion and to work out what would be the final velocity of ball B just before it hit the ground. So using VB squared, VB final squared equals VB initial squared plus 2AB delta XB. We know that VB final squared is unknown. The initial velocity that it was thrown down was minus 5,98 squared plus 2 times minus 9,8 for A. Delta XB is minus 43,76. See there? H is 43,76, but remember, delta X is downwards. So it's 0 minus its initial position, or thinking of it as delta X as a vector, which is pointing downwards, and its magnitude is 43,76. We can see it there again to emphasize. That's the direction of the vector. In the negative direction, magnitude is h. So doing that, we find that working out that the final velocity is 29,89 plus or minus. Remember, if you square root both sides, you get plus or minus. But this is clearly moving down, so we choose the minus. So the final velocity is 29,89. Sorry, I apologize for that. Is 29,89 meters per second downwards. And whilst it's not necessary, we can just check. If we use VB final equals VB initial plus A delta t, where VB is minus 29,89, the initial velocity is minus 5,98, acceleration is minus 9,8, and if we solve for delta t, we get the 2,44 seconds. So I've done this so that we can draw the graph later on. And so you also can see that these equations all work together and they tie into each other. So with this now, let us move on to the next question. Here we are asked to sketch the velocity time graphs for the complete motions of stones A and B on the same set of axes. Label your graphs for stones A and B clearly. Show the following on the graphs: the time taken for stone A to reach its maximum height, the velocity with which stone B is thrown downwards. Now, first things first, it's a velocity time graph, so we label the axis. Stone A starts at plus 12 meters per second. We're using plus, according to our sign convention, plus is up. Stone B starts upwards at plus 12 meters per second and is decelerated until it reaches 0 meters per second after 1,22 seconds. Notice the negative gradient, and that's because the acceleration is minus 9,8 meters per second squared. Over 1,22 seconds, it falls by 12 meters per second from 12 to 0. This is right at the top where it stops momentarily before it changes direction. As we can see, the velocity goes from being positive to negative, but the gradient still remains minus 9,8 meters per second squared. We then look at stone B. Stone B starts with a negative velocity of minus 5,98. It too has a negative gradient, and these two gradients need to be the same because they are both minus 9,8 meters per second squared. So these two lines need to be parallel to each other because both of the stones are under free fall. They are both They both have an acceleration of minus 9,8 meters per second squared. Stone B starts at minus 5,98 meters per second, and as we worked out, after 2,44 seconds, it travels at a maximum velocity of minus 29,89 meters per second downward. And right here at this point, the ground touches the ball, and then, as you will see with bouncing balls, which we're going to do a little later on, there's other physics that happens here, because now a net force other than gravity acts on the stone, and so what happens now, there is a radical change in the velocity of this stone and also the shape of its velocity time graph. We'll get to that a little later on. Stone A has had to travel further, so stone A at 2,44 seconds, stone A is actually only where it originally started. So this area and this area, if you add them together, that's going to be a positive area, this is a negative area. These two should add up to 0, because at 2,44 seconds, the stone is now traveling downwards, but it's now come back to where it originally started. So its total change in position is just 0 meters. So, but stone A then carries on after 2,44 seconds until it eventually hits the ground. And we'll see in the next slide, when we draw the other two graphs, how this makes more sense. So here's the velocity time graph, as we've just drawn. And now, if we look at the acceleration versus time graph under it, stone B falls for 2,44 seconds, stone B falls for 2,44 seconds, and its acceleration is minus 9,8. We haven't worked out the total time that stone A travels, but this is a sketch graph. We could work it out. Interesting exercise to do. But at this time here, stone B comes to rest. Now we've got to be careful. The velocity is not going to, is it going to be the same? It's not necessarily going to be the same, because it's going to actually be a little bit more, because at the time that it is at the height of h, its velocity downwards is minus 12 meters per second. So we are, in the sketch graph, from a sketch graph, not 100% accurate. It's just a basic shape. So, but what we do know in the total time that stone A is traveling, its acceleration is also minus 9,8. Now, if we go to the change in position, what we do know is the following, that both graphs are going to be parabolas, because stone A and stone B are both accelerating. They're not traveling at constant velocities. They're accelerating. Stone A starts at 0. All right, now in actual fact here, I've made a little bit of a mistake, and it's okay, I'll show you. I've made a little bit of a mistake because in actual fact, I have changed what I defined as x equals 0. In actual fact, I defined x equals 0 as on ground level. So in actual fact, if I look at this should be different. And it's good to show you mistakes, because then you learn from them. So in actual fact, this should be where x equals 0 is. This is h. So this is plus 43,76 meters. And this should be 43,76. So if we take 43,76, old school, we add using manual method, plus 7,35. 6 plus 5 is 11. 1, carry 1. Yes, I come from a previous century. I still add like this. 1 plus 7 is 8, plus 3 is 11. 1 plus 3 is 4, plus 7 is 11. And this 1 plus 4 is 5. It may be old, but it works. This should be plus 51,11 meters, and this would be x. So I made a mistake in my position time graph because I changed my x value. Don't do that. You can see the shapes of the graph are still the same. The change in position, sorry, not the change in position, the initial position for the stone A is now 43,76 meters. Over 1,22 seconds it moves up. Notice that the gradient of this graph decreases as it moves to the point where it's going to be at zero velocity, right at the top of its motion, at the maximum height of 51,11 meters above ground level. Then it now changes direction. The velocity is now negative. It goes from velocity equals 0, and it becomes, the slope now becomes increasingly more negative. If we look here, it becomes increasingly more negative. It's initially x equals 0. It's negative, and it becomes increasingly more negative as the velocity becomes more negative, because the velocity is the gradient of the curve. And after 2,44 seconds, it's back at its original position with respect to x equals 0. So that's stone A. Once stone A reaches x equals 0, now if you look here, and we learn by making mistakes. If we look here and I go now and I draw, which is what I should have done, if I go and draw a line down like this, then you'll see that in actual fact I should have stopped my graph here. I should have stopped my graph here, because at this point here A hits the ground, as opposed to here where B hits the ground. So we must just be aware of the fact that we are working with sketch graphs, and so they are not according to scale, and so they are inaccurate. With stone B, we see that it starts at 43,76 meters above the ground. It doesn't have a initial velocity of 0. It has an initial velocity of minus 5,98 meters per second. So its initial gradient is not 0, it's not horizontal, so it's got a bit of a slope, and it gets increasingly steeper in the negative way because the velocity is increasing in a negative direction. We can see it gets increasingly more negative. And both stones, as we've said, are both going to stop at minus 43,76 meters. Sorry, not, yeah, that's with respect to 0, but both stones will stop at x equals 0. So that's enough for now. I do apologize for the fact that the graphs are not as accurate as I would have liked them to be, but the idea here was to give you an idea of what the shape is. And as you can see with accelerated motion, when your accelerations are negative under the influence of gravity, we get position time graphs that are parabolas. It gets a bit more complicated when you start working with two-body problems. You've got to be very, very sure that you've defined your positions with respect to a specific frame of reference, as we did, it's at ground level, and that your values are accordingly correct. We see that the two velocity time graphs are both straight lines, and they both have negative slopes because the gradients should be negative, because gravity, they are accelerating under gravitational acceleration. Down is negative, so the sign would be minus, so they've got negative slopes. If you had defined up as negative and down as positive, then these graphs would have run in the opposite direction. when you go through grade 12 papers, you will see that they invariably give alternative solutions based on which direction you define as positive and which one is negative. Note that both of these must be parallel to each other because of the fact that they both have the same gradient, because they have the same acceleration. So now that we've done all of this, and this was way past what the question actually asked, but it's good to do because it helps us to get a deeper understanding of the relationship between the graphs, the equations, and the motion. We're now going to go to the next type of problem. So on Classroom, I will post a past exam question which involves bouncing balls. Now, I just want to spend a minute or two on this just to give you a little bit of a deeper insight into what you're seeing here, and in order to help you to solve the problem. So if we look here, this is a velocity time graph. As you can see, velocity in meters per second and time. And so what you get here is you've got a, and there's a problem here. This is not minus 40. This would be minus 40. And this would be 40. So what we have here is the initial position of the initial velocity of the ball is, let's call that A, is plus 40 meters per second. All right, and then what happens, the velocity becomes 0. So it seems as if the ball is projected upwards from A, and at point B it has a 0 velocity. This is the ball. We can see that the gradient is negative, and the gradient must be acceleration because we're dealing with free fall. So down is obviously negative, and the acceleration is going to be, let me just move this out the way here. We have got acceleration is going to be minus g. We can tell from the backward sloping velocity time graph. So at A, its projection velocity is plus 40 meters per second. Then when it gets to B, it's at 0 meters per second, as can be seen. And then on its way down, it comes to C, point C, where it's traveling at minus 40 meters per second. So our sign convention, up is positive, down is negative. That's our sign convention. Now something strange happens. Suddenly, from C to D, at 8,16 seconds, the direction changes. So this is where the bounce takes place. This is where the bounce, this is the first bounce. Because what happens is, and once we, in metric, when we start to take the time interval into account, there, we will then find that where the graph is there and where the graph is there, it's not directly, D is not on top of C, because there's a split second of time in which the ball, when hitting the ground, is decelerated and then accelerated so that it leaves in the opposite direction. So when this ball leaves now, so this is C, you can think of D as where the ball now, it would be at the same position, but now D is where the ball leaves at a smaller velocity. And so you can see here, this velocity at D is smaller than at A, and that's because there's a certain amount of energy that is lost in the collision with the ground. Now, once the ball leaves, It moves up again under the influence of gravity until it gets to point E, where it's once again 0 meters per second. And then it's going to accelerate downwards again. It's going to continue. It's going to accelerate downwards. By the way, ACD, we're not going to work with the horizontal displacement. So you can kind of assume that it's all going to be in the same position, but we're writing them next to each other just to make it more visible for us. So when it gets to point F, we see here, point F, the value of the velocity here will be the same as there. It'll just be the negative because it's in the opposite direction. So this is point F. And point F here, at point F, this is where the second bounce occurs. So this would be the second bounce. And if this were to continue, you would see now that when it leaves, it would be at a lower velocity than what it was at D, which is lower than A, and it would look like this. If you can just, for instance, also just look at the area under here, and the area under here, you can see this area is bigger than that area, which means that this height is bigger than that height. And that's what happens if you take a tennis ball and let it bounce. You'll see that with each successive bounce, energy is lost, and so it doesn't bounce as high until eventually it stops bouncing. And this is exactly what's happening here. You will see that this is in actual fact the height h, and that height is going to get smaller and smaller and smaller after each bounce. So this should be enough in order for you to be able to launch into the problem that I will post on Google Classroom for you. So I hope that this video has helped you to gain an even deeper insight into vertical motion and into two-body problems.